Professor Dhar did his graduation from Allahabad University, followed by a master's degree in physics from IIT Kanpur. He then moved to the California Institute of Technology for his PhD, after which he returned to India and joined the Tata Institute of Fundamental Research in Mumbai, where he spent most of his career. After his retirement from TIFR, he served as a distinguished professor at IISER Pune. He is currently an INSA Distinguished Professor at the International Center for Theoretical Sciences in Bangalore. Professor Dhar has made many pioneering contributions to the field of statistical mechanics, some of which include his work on self-organized criticality, disordered magnetic systems, fractals, and percolation theory. He possesses a deep physical insight in combination with an exceptional command of on mathematics, which have enabled him not only to propose new models, but also to provide exact analytic solutions to challenging problems in the field of statistical mechanics. He has received many recognitions for his work, which include the Boltzmann Medal, which is awarded by the International Union for Pure and Applied Physics, and which is the highest honor in the field of statistical mechanics. His other notable awards include the Padma Bhushan, the Shanti Swarup Bhatnagar Prize, the J. Robert Schrieffer Prize by ICTP, the TWAS Prize by the World Academy of Sciences, the SN Bose Medal, and the JC Bose National Fellowship. Professor Dhar is also an elected fellow of the major Indian science academies, which include the Indian Academy of Sciences, Indian National Science Academy, and National Academy of Sciences. It has been my good fortune to take courses and have discussions with him since my PhD in TIFR. Apart from his brilliance and sharp wit, what leaves a deep impression is his willingness to patiently explain and discuss physics with scientists, irrespective of their age or stature. It is a pleasure to invite Professor Dhar to deliver his lecture on transience and freezing involving sokobans moving on lattices.
Okay, thank you, Apurva. Thank you. Is it good enough for you, or should I? Thank you, Apurva. So today I would like to discuss some model problem. It is a mathematical toy model, and the interest in it is because what we like to do in physics in general is to take. Okay, thank you. Yeah, it's working. Okay, so what we like to do is to take up some system, but then you have to get rid of the complications and make the model as simple as possible, and then try to understand that first. Once you do that, then you can add complications later. So sometimes the simple models appear rather artificial, and sort of famous snide remark about them is spherical cow approximation. Okay, but actually it is outside this, but let me just mention this, it is interesting story. The spherical cow story is actually a nice story. There was an Arab sultan or modern sheikh, and he had a stable and lots of horses, and he wanted to have them fed and race and all kinds of stuff. So he appointed some scientist, medical doctor, to fix the diet for these horses. So he had to decide how much food they should eat per day. And then he did some calculation, they need so much heat to be exposed or something. And he said, for our purpose, all that matters is how much heat you have to radiate per day. And it is a good approximation to treat the horse as a sphere of a particular mass. And it turns out it's a actually a pretty good approximation. You can do the same thing with goats and horses and rabbits, and the energy requirement turns out to work out quite well in this system. So for his purpose, it was good enough to treat the horse as a sphere. It's not a stupid approximation. Of course, it's not telling everything, but for my purpose, it is good enough. Okay, so that is the story. Even if you don't remember anything else about this talk, you may remember this story. Okay, so let me discuss this one. I will discuss, transience and freezing. Transience is sort of some word, but transient you have heard before. You know, people do experiments with capacitors and something, and there is some, when there is an electric circuit, you turn it on. Initially, there is some funny current, and after some time, there is a steady state. The initial state is called transient. So something which doesn't survive forever. And then the other word is freezing, which you know, the things just get stuck into something. And these are very general phenomena. And this particular stuff later is a model of which incorporates these features. So we will study this model, but some of the discussion or some of the results will be applicable in a wider context. So that's the general idea. Okay, so this work is done with Priyadarshini. She is a student at ICTS, and IIST Dhar is also a collaborator, but a professor, and some discussions with Diptiman Sen at IISc. Okay, so there is so before I introduce the model, there is you know, the motivation for the model. Why are we studying this particular problem? So there is a lot of history, and I cannot give all the history here, but just indicate the basic line. So the initial problem, which everybody kind of can appreciate, is fluid flow in porous media. So there are things like rock and water has to, you know, it seeps through the rock and reaches the bottom, and people want to know how much time it will take or how it will go. Or there is oil in the rock, and you know, you have to push it out or some such thing. So fluid flow in porous media is a very big topic, very important for applications as well. Just 1 minute. I forgot to mute this earlier. Okay, so oil recovery is, I told you, example. Filtration is another very common industrial process where you have to study fluid flow in porous media, like filter paper or some more complicated stuff. Sand is used as porous media in which you drop something from top and filter water from sand, right? Stuff like this. And so people have studied this for a while, and there is a very famous model by Dijon called the ant in the labyrinth model. Okay, so what he said was that the porous medium has some holes and some regions where you can go, so it can be modeled as a labyrinth. Okay, and fluid particle is something like an ant which can move in some allowed region and not in some other region. And what kind of motion will this have, or what kind of effect will the fact that everything is not allowed, all moves are not allowed, will have on the motion of the ant? Okay, so this system is in which there is the medium is taken as a static medium, and a single particle moves in a static medium. And what happens? That is the general problem. And of course, this is kind of fairly well understood. Let me just say qualitatively, if the medium is such that there are some small pockets which are not allowed, but rest of the stuff is allowed, then the particle can go everywhere. It avoids those small holes, but it's diffusive. R squared goes as T. On the other hand, if the most of the space is disallowed and some pockets are allowed, then the motion is confined. And so there is a transition from confined state to unconfined state, and that is what was studied by Dijon. And he showed that this problem is equivalent to some other problem like the resistor network problem or whatever. But there is another model which is also very well known model of diffusing particles. It is called Langdon ant model. So in the Langdon ant model, it is a model in computer science. And what they say is there is a grid, and there is one ant which moves on this grid. But this ant is a tiny robot. It has a computer program in it. So it says, look at the square you are in and look at the color of the square. Things can have several colors. If the color is red, then move east. And if the it moves to nearest neighbor depending on the color. But it has an extra instruction. We said before moving, change the color. If it was yellow, change it to blue. Okay, so it changes it to blue, moves here, then it looks at the color here, does move appropriately, and then change the color here, and it keeps on moving. But after some time, it will come back to the previous square where it has already been. And now its motion is different from before because it changed it. So in this case, the medium is modified by the motion of the walker, while in the first case, it is not modified. And it leads to very interesting additional features which are interesting to study. Okay, and this one is actually not too much theory is known about this. This model was defined by Langdon around 1960 or some such thing, but it is still, it's an evocative model, and it is sort of intellectual prehistory of our model. Okay. So now we come to this model of sokobans in a random medium. So sokoban is a Japanese word for a storehouse keeper. So sokoban is just a person who keeps, manages a store. And there was a model of this which was introduced by Bonomo in 2024. We are not the inventors of this model. And but we made some variations, which I will discuss next. Okay, so in this talk, I will discuss the model of many sokobans on a line. So there is a line, there are lots of sokobans, they move. And there are some boxes which the sokobans can push. Okay, and which the model will be defined more precisely later. But what we want to discuss is that what happens if you let this thing evolve in time. So it turns out that you see some transient behavior. There are some configurations which are there, but which are not found later. So the state of the system changes with time, and some things are lost, they don't come back again. And so that is, how fast does that happen? That is transience. And steady state, what is the long time steady state of this system? And it's just a model of interacting systems in which you have a lot of diffusing particles which move around and they modify the medium they move in. Okay, that is the general philosophy. So this is of interest because it is analytically tractable model of self-generated disorder. So what happens is that there are these things which move around and they push the boxes, but eventually they push the boxes in a place where the boxes cannot be moved anymore. So it is a quenched, the disorder becomes quenched, but I didn't put them in there. So it is self-generated. And of course, self-generated disorders are easy to design or make models of, but tractable models, where you can calculate or some such thing is harder to do. So that is the aim of this. I won't go into too much algebra in this talk, but it can be done. And it doesn't, in order to understand what happens in the problem, you don't have to know all the algebra in gory detail. You want to learn, you can learn, but you don't want to learn, you can still understand the interest in the problem without all the algebra. And this is also another word which is common, strongly broken ergodicity. And so there are systems in which behave nicely, and there are systems where so-called ergodicity is broken, all states are not available. They are called glassy systems or some such thing. There is a lot of literature about these. And of course, several thousand papers, I guess. But quite often it is not very tractable analytically, or you cannot make theoretically exact statements about them. And my sort of interest is some interface between interesting problems and tractable problems. And so that is what we will try to do here. Okay, so Sokoban is a video game invented by Hiroyuki Imabayashi in 81. It looks like this. You can download this from the internet. Just set Sokoban video game. It will come free. And the game goes like this. There is some region like this. And there is this guy. This is called the Sokoban. And using your fingers, you can make this guy move left or right, up or down, one square at a time. And when it comes to here, it cannot go to space which is already occupied by something else, but it can push this box and come here. Okay, and so it can push a box and go there. But if there are two boxes adjacent to each other, then it doesn't have energy to push two things at a time. It can only push one box. Okay, and the aim of the game as such is that put all these yellow boxes in these designated spaces which are shown by red crosses, and if you do it faster, you get more points. So in this one, there is some question of strategy. You know, if you want and you have to plan your moves and you have to do them fast and so on and so forth. We are not going to worry about that part of the problem. Okay. So then we come to this model which Bonomo et al. Introduced. So they introduced what is called a blind sokoban. So this sokoban doesn't have any memory, doesn't have any strategy. It just moves at random. If there is a space, it tries to go there. If it cannot move there, it just stays put and tries again to some other direction. At each time step, it will try in some direction. If it can move, it will move. It can push a box, it will push a box. If it cannot do it, just stays put. Okay. And then, you know, if there is some other way to move, eventually it will find it and go there or some such thing. Okay. So actually it will move if allowed. This is the end of the definition of the model. 2 lines. Can push an obstacle to the side in the direction of motion. So if the box is here, you can push it like that, but cannot push it that way. That's the model. And since the sokoban can push objects out of the way, one would expect her to get trapped less often than a blind. Division ant model. If there are too many boxes, then the guy is trapped and it cannot push anything much out. And there is a finite set of spaces available, it keeps on moving between them. But if the density is low, then it can go very far. Okay. But here, since this sokoban can push boxes, you expect that it will be trapped less often than otherwise. That is the naive expectation. And they found that this is not true. The fact that it can push, it traps less often is true when the density of obstacles is high. But if it is low, then it turns out that it's still, the blind ant would have been able to go everywhere. This ant gets trapped all the time. Because what happens is that it takes all these boxes, moves at random, pushes them out of the way, usually outward on the average. And then all these boxes are pushed outward. So there is some radius r. The boxes are on the perimeter of this, and they form then a wall of depth 2, and then they get trapped. So it traps itself. It pushes the boxes out of the way, but pushes them into place where they form an impenetrable wall. It gets trapped. And the interesting point is that it is trapped for all densities of boxes. If there is 1% boxes, eventually it will push them out into a big circle. And in the circle, the perimeter has much less size than the area. So even 1% of the box, you know, if the radius is more than 200, then the perimeter will not, you will be able to form a perimeter of depth 2 with only that many. So it always gets trapped. So that was the surprising thing. So this is what it says. Sokoban traps herself with probability 1 on a square lattice. This result has not been proved analytically, but based on their numerical simulations, they conjectured this. That is why this thing occurs with a question mark here. Okay, but anyway, that was the model they studied. And this is their result, So they said this is, this is the mean squared deviation as a function of time. Initially, it is kind of diffusive and then saturates. And for different densities, it saturates to different values. Nothing very surprising there. This is, once it has got trapped completely here, I gave the argument with circular shape, but the shape is not actually circular. It is much more complicated. And here, in this particular thing, it can move in this blue region, but that's all it can do. It cannot get out. It is fully trapped. Okay. And this requires explanation or understanding. Mostly numerical. Okay, so we will consider a slightly different problem because this model, of course, has already been published. So what can I do about that one? So we considered a model on a square lattice, let us say, or on a line with many sokobans. And there is a density of sokobans, there is a density of boxes. You put them initially at random. And a configuration is specified along the line with this E, S, E, B. E is empty, S is sokoban, B is a box. So you have a long line and each side has one of these three states. So you specify its configuration by a string like this. The allowed transitions are ES can become SC, that is the sokoban can jump, or SBE can become ESB, push or backward. EBS can, it will push that way. ESB cannot become SBE. It cannot pull, it can only push. Okay, so how to characterize the long time steady state of this system? You imagine that there is a very big box. Then what will happen? Can you say something qualitatively about this behavior? Okay. Yeah, no, very good. So, no, the boxes have a finite density. So, I'm imagining a system where there are thousands of boxes. So, what will happen? Okay, something like this. No, very good. So, but let's see. We'll go on. So actually, in the beginning, let us do work with 1D, and then you will see that some of the conclusions will continue to be valid even in 2D. Calculations are for 1D, but the qualitative behavior is valid also for 2D. Okay, but 2D we don't have very rigorous results. Okay. Okay. So on a line in 1D, the behavior is easy to predict. So this is a problem which, with a little bit of thought, a high school student can study. So what happens? If you start with the configuration of sokobans and boxes, there will be stretches with more than 2 boxes between 2 consecutive sokobans. So, there is a sokoban box, an empty box, box, and sokoban. There is some stretch of boxes between 2 sokobans. Then the rightmost of these boxes can only be pushed in by the sokoban, and the leftmost can only be pushed to the right. So that spacing between the sokobans will keep on decreasing with time, right? And finally, we will have a structure something like this. There is a sokoban here. This box has been pushed near this box. That box has been pushed near the other box. But now these are 2 boxes. They cannot move further. They are stuck. They will be stuck forever. These in-between spaces, they cannot be removed now. Okay. So this much is easy to see. A question would be that can you tell exactly what fraction of stuff, what will be the exact density of these or that or some such thing. So once there is a region of these and empty spaces bordered by impenetrable walls of double boxes, these boxes get frozen and cannot move in future. So if you have this one, this B can be pushed here, this B can be pushed here. In between these if there is more B inside, they will just stay put, they cannot move. So we would like to know what is the fraction of boxes which cannot be moved at some time or some such thing, right? Okay, so the line gets divided into active regions of sokobans and empty spaces and singleton boxes, alternating with frozen regions of immobile boxes. There's some region in which nothing can move, then there's some region in which sokoban can keep on moving left and right. There's another frozen region, another active region. That's all that happens. But what is the statistics of these active regions and frozen regions? That is what we would like to understand. Okay. So there is a strong breakdown of ergodicity. These are just words. But what it means is that there is a set of states available to the system. But if you are in one point, you cannot access all the other states in the system. If you can access, it's called ergodic. And if from this state you cannot go to all possible states even after a large number of moves, then it is called non-ergodic. There is some famous ergodic theorem due to Birkhoff, which says in dynamical systems all parts of phase space are visited. Then it is ergodic. And if they are not visited, it is not ergodic. So here they are not ergodic. So the phase space breaks into large number of mutually disconnected components. So there is some set of configuration. From here you can go here and keep on backing, but from here you cannot go here. But from here there is a set of configuration to which you can go. So the system breaks up into a large number of disconnected components. So now I say, suppose I start with a system of size L. How many components will be there? Okay, so if I have a system of size L, there are 3 to the power L configurations possible because each site can occur in 3 states. And so here, the total number of configurations is 3 to the power L, and the number of disconnected components grows exponentially with the size of the system. And it grows faster than 2 to the power L. We have a huge number of disconnected components. So what is the, how can I prove this? So the answer is, suppose there is a phase space with lots of components, but there are configurations in this phase space 3 to the power L, in which there is no sokoban, only empty sites and boxes. Each of them is a component of size 1.
3 to the power L is with density fixed or?
No, this is with arbitrary density, total. And is 2 to the power L. And each of them is a single configuration component. And so the total number of components with everything allowed has to be bigger number than this. So it's bigger than 2 to the power L. Okay? Okay. So now we sort of come to this other question, existence of conserved quantities. So this is a model. Does it have some conserved quantities which are conserved? Because in dynamics, people are very happy to identify constants of motion. So clearly the number of boxes is conserved in the dynamics, and the number of sokobans is conserved in the dynamics. These are constants of motion, right? So the phase space will break up into so many boxes and so many sokobans, and that will be one component, and this you cannot go from here to there. But this number of components is only, the number of boxes is at most L, and number of sokobans is at most L. The number of components you will break this into is at most L squared. But the actual number is much, much bigger. It's 2 to the power L. Okay. So with these constants, with 2 constants, you can only construct order L squared mutually disjoint. So there must be many more constants of motion. Okay, there is another part which says that suppose there is a component, then you can, this will always stay in this component. So if you label the components with integers, then the label is a constant of motion. Okay, and but writing algebraic formulas for those labels is non-trivial. So, but there are many more constants. For example, the relative order of S and B's cannot be changed. Okay, so we define an irreducible string of a configuration by constructing a string, space, deleting all occurrences of e's in the configuration. So you start with the configuration, get rid of all the E's, then you get a string of S and B. Whichever configuration it goes to, it will have the same string, because only the relative position of E's can change by the dynamics. So the string is a constant of motion. How many strings are there? The number of strings is, okay, maybe it's in the next slide. No, it's not here. So the number of strings goes as 1.6 to the power L or some such thing. It goes exponentially with L. So, from the square law L squared, we have got to e to the power L, but can we construct all of them? That is the question. So clearly the IS is a constant of motion, this irreducible string. Graph on the set of vertices denoting different configurations. So this is a picture. You make configurations.
You give an algorithm to construct this.
Yeah. So that was the algorithm. I already gave it.
That's identifying
String. Take the initial configuration, get rid of all the E's. Whatever remains is the irreducible string, which is conserved. Okay. So the definition of irreducible string is exactly this, and it is conserved. Okay, and it can be used to distinguish between two.
You were saying about the number of possible
Yeah, that's a separate calculation that can also be done, but that we are not doing here, but it can be done. Okay, so breakup of phase space. So this is what we are actually trying to understand. So breakup of phase space occurs in 3 stages. That was the reason for introducing this model, let us say. At first stage, the graph breaks up into disjoint components such that there is no edge from one component to another. So I'm here, or there is a set of edges, a set of vertices here which are connected to each other by directed edges. But from this, there is no edge to okay. So disjoint components such that no directed edge from one component to another. This is quite clear, that's just in the graph there is a notion of disconnected graphs, and that's the notion we are using. So that's called the first stage of breakup. Now you look at one of those components. In the second stage of breakup, using irreversible nature of some moves, we can organize the configuration within one connected component into levels. So now I look at the arrow directions, I see, oh, this one can go here but cannot go back. Then it turns out that you can, and I will not prove it here, that you can get them into levels r equal to 0, 1, 2, 3, such that a configuration at level r can only stay at the same level, or it can go to a lower level. It cannot never go to a higher level. Okay, that is because there are no loops possible. You cannot have a set of arrows which go back to the same place. Okay, so at r equal to 0 level are the recurrent configurations which will stay there. If you are at r equal to, so that's a transient. So then, yes sir, r is the level index. The levels are organized into heights, r equal to 0, 1, 2, 3, 4, 5. It is an index for the label for the height of the level.
how much a sokoban can move?
No, not how much. There are set of configurations, but they are broken into levels such that from this level you can only go down, you cannot go up. Okay. So how many are there in one level, that we are not discussing here just now. Okay. So within the same level, now I look in one level and see, what is this. So then again they break up into connected parts and disconnected parts within the level. So that is called the third level of decomposition, breakup of phase space.
How do you define the level?
Which after 2 steps can go into something which will not be able to do. Okay. So here is a picture of the same. So these are the configurations denoted by green dots. And if you label them like this, it means that these are connected to each other. You can go from anyone to anyone. From here you can go which are totally separate, disjoint. Okay, so that is the first level of decomposition. At the same level, that is the second level of decomposition, and within the same level and within the same component, you can have further sub breakup. So that is the third level of decomposition. Okay. So this is an explicit example, with 6 things and some particular sub. You don't have to look at it very carefully, but if you want, you can. It's there. Okay, so now we want to quantify this level decomposition, and I'm only indicating the argument. It says the first level of decomposition. We just want to say, are things connected or not connected? So at this stage, we are just saying, is there a bond between this and this or not? So it is convenient to make all the bonds reversible. So you study a different problem in which the sokobans can also pull boxes and not only push them, right? Then what happens, that these arrows which were drawn earlier, they are made two-way arrows. Okay, and in this case, still there are extra conserved quantities beyond the irreducible string. And if there are 3 boxes one after another with only empty spaces in between, then the position of the middle box cannot be changed in time. Okay, so it is like this. So suppose you have a string like that. There is an S, B, 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 something. Then these B's cannot actually ever evolve in time. By just looking at the string once, I can identify these boxes will never move. Their position is a constant of motion. Okay, so the positions of B's in the IS of parts between B's are separately conserved, and so this you can show that these are, if you identify the irreducible string and the position of B's, then you actually give all the full decomposition at this level, and the number of components grows as 2.2 to the power 8 L. Okay, this I will not do here, but it can be done. Okay, and we are able to determine exactly the number of disconnected components using generating function techniques. So L is 1, 2, 3, 4, 5. These are the number of components you can get. Okay, and there is some explicit formula for these, of course. Stage 2 decomposition. Now we note that if there are 2 boxes separated by only empty spaces, and there is at least one sokoban on either one side, then this spacing can only decrease. If there are 2 sokobans, but there is no, the 2 boxes, but there is no sokoban in between, then this spacing can only decrease. Okay, so I define the height of the configuration as the number of empty spaces of this type, and this can only decrease in time. So this number becomes the level index. Then you just ask how many things are there at level H is how many things are there with this constraint, that means the sum of all the B's of this type should be this, and this can be done, and we can determine the number of configurations at a given height. That calculation is a little bit harder. I will not do the calculation here, but you can do it like this. So this L equal to 1, there are 3 components, and they are all conserved, they cannot move. There is only L equal to 1, nothing can be done. Here there are 9, and here there are 2. So this is at level 0, and this is at level 1, and this is 0, 1, 2, 0, 1, 2, 3, and like that. So this is the last time I had just the total number here, 6313. Now this 6313 has been broken into components, like that. Okay.
So for each L, you have to solve some combinatorics.
Yeah. So for each L, you will have to find what are the different numbers, how to fill in this table, and it can be done. That's a little bit involved calculation, but it's an explicit calculation, it's doable. Okay, and we can determine. So this is the density of contractible spaces, rho. So there is in statistical physics, we normally have things like conjugate variables or Lagrange multipliers or some such thing. If you want to find something with so many constants, you construct a Lagrange multiplier lambda, and then solve it for arbitrary lambda, and then fix lambda so that you get the particular density. It's a complicated technique, but here as a function of lambda, you can adjust the number of contractible spaces. So if you want density of contractible spaces to be 0.6, then I know what lambda to put in and how to calculate. And you see, this one is a little bit complicated, but anyway, configurations at height 0 are called recurrent configurations. They will keep on coming back again and again to the same subset, and their number grows as 2.86 to the power L. So it's less than 3 to the power L, which means that each component will also have an exponentially large number of, not each one, but many of them will have exponentially large number of configurations in one component. Okay. And sorry, here you can give the log of the number of configurations as a function of fractional height. So the heights we showed in the first graph, sorry, this one. So how do these numbers change with height? So this each of these numbers is roughly exponential in L, but that coefficient varies with height. And how does that vary? And that graph goes like this. It's an exact calculation, but we are not doing this here. So initially it goes up and then it goes down. If you say the number of contractible spaces is 1, means almost everything is contractible. Those are the configurations, means there is a B here and there is a B here and one has some place and nothing else. So almost everything is empty contractible space, and it will be pushed out in the end, and it will go to 0. So if you are here, you go, in the end you end up with no contractible spaces. Okay. So stage 3 decomposition. I'm just giving an idea of how these calculations are done. So consider a configuration like E, B, E, something, something. In this case, we denote a contractible empty space by big E. This is a contractible empty space.
So
yes.
In the last graph,
yeah.
Is the maximum.
Yes.
What?
Yeah. So the maximum, the value here is log 3. So it is equal to the entropy of the maximum possible space, so, but this density is 1 by 16, we can show exactly, but I'm not doing it here. It can be done. We can determine this whole graph exactly, and the detailed properties can be determined, but those are specific to the model, and if you study some changes, then it will become different. Okay, so in this calculation at fixed level H, we count all configurations with the fixed IS with positions of B's and number of E's. And the third level of decomposition, position of all the E's are also constant. Suppose you say E's are also fixed, they cannot change. Then you are additional constraints of motion, they give you extra decomposition. And this number then goes as 2.55 to the power L for larger. You can calculate these numbers exactly. Okay, so extensions. One can study this model in higher dimensions. That's what we discussed in the beginning. We have some results of simulations in d equal to 2 and some random layered graph, which is effective dimension infinite or some such thing. One can also, so in d equal to 2, standing here, what can I tell about the system? So in d equal to 2, it happens that if you have a 2 by 2 square of boxes which come together to form a 2 by 2 square, now it cannot be pushed anyway. Nobody can move it. So then it gets frozen. So there are analogues of these frozen configurations in 2D also, and also in 3D. In 3D, it will be 2 by 2 by 2. In any direction you try to push, it will not be able to push. Right? And so you can study. The phenomena is pretty general, but exact calculation of the numbers may not be so easy. In any case, we can also determine the breakup on the entropy of the system, or the frozen entropy and dynamical entropy. So that gives, so this was the main reason we got into this particular question, is that there is a phase space. There is some number of configurations available, but there is a strong breakdown of ergodicity, right? So from here you cannot go everywhere. So how many places can I go to? That is called the available number of configurations to me, accessible entropy. This also is usually proportional to the volume, but the coefficient is different from the thermodynamic entropy, where you would assume, or ergodic entropy, which you will use if you assume that all the phase space was accessible. And in this particular model, you can calculate this accessible entropy. And in most other models, you cannot calculate it. So, for example, people can calculate the number of configurations, but what, there are in all these components in this picture. The number is not the same in different components. So what I'm interested in generally is, if I go to a random configuration, how many components will there be in a typical something like this, in a typical blob? So there is a distribution of sizes. But what is the most likely size? Turns out that if you the most likely size, which is the same to leading order. So what is that coefficient in front? That calculation is usually hard in most models, but it can be done in this one. Okay, so I'm nearly there. Summary. So we defined a simple toy model of interacting diffusing particles, which modify the medium as they move. Okay, that was the thing we were trying to study. And just for everyday application, I just mentioned about the filter paper, and so you take coffee, and the usual phenomena people encounter is clogging. But clogging is the medium is modified by the things which are going through it, no? So, these kinds of models that's the general motivation for understanding some such stuff. So, they modify the medium as they move. That's the point. Vision is interesting, but it's not enough for us. We would like to study cases where the ant can modify the medium. And this dynamics produces strong breakup of phase space into disjoint sectors. And we can characterize this decomposition in some detail. And in terms of constants of motion. So that is a more general notion, that whenever you have this phase space decomposition, you can define constants of motion, or vice versa. If you have constants of motion, then there is of course phase space decomposition, in the sense with one value of constant you cannot go to another value of constant. It's a constant. Okay, but this is a two-way stuff. And so if I give you the breakup, can I design constants? Can I infer the constants of motion from the breakup? That is the question. And this space can be useful in the study of other glassy systems. And nowadays there is a lot of work space fragmentation. So I don't know what this is, but they have some many body system. It evolves using quantum mechanics. So that's the main difference, is that the evolution is quantum mechanical. These are quantum mechanical models. There is a phase space, but you evolve using a Hamiltonian. The Hamiltonian is given to you. It goes into a set of states from a given state, but it doesn't go to the full phase space. It goes to some small part of the phase space. And if you start with some other configuration, it goes to some other part of the phase space. And so if you write the Hamiltonian as a matrix, it will have a block diagonal structure. From this configuration, you can go to this and this, and so people want to understand the block diagonal structure. It's called Hilbert space fragmentation, because there was a Hilbert space breaking up into smaller Hilbert spaces. And it is called strong. Strong means that the number of components grows exponentially with the size of the system. Okay, and so here we have a classical mechanical system which does the same thing. There is a Hilbert space fragmentation here, because if you write the evolution matrix, or as a matrix of adjacency matrix for the graph, it will also show the Hilbert space fragmentation. Disconnected components, you can write them so that this part is not connected to that part, right? So whatever techniques we use here can also be used there, or have been used there, or just cut and paste structure. Okay, and so I think that's the end of this. I'm happy to answer questions if you have any. Yes, sir. Yeah, so in this system, so actually most of the discussion remains the same, whatever boundary conditions you use. If you want to calculate these numbers, they will change if you use different boundary conditions. The reported numbers are for periodic boundary condition, but it can also be done for open boundary conditions. Yeah. So no. So all the calculations were done for finite L. I gave L equal to 2, 3, 4 tables. So they are not starting with the thermodynamic limit. For each L, you can calculate the structure, and of course it depends on the details like boundary conditions, but it can be done for all reasonable boundary conditions. Okay. So we can do it on different manifolds like on a torus. Yeah. You can do it on different manifolds. The Sokoban model can be defined on different manifolds. They are not defined on manifolds; they are defined on grids. But you can make different grids, and you can define the model on arbitrary grid. Yes.
For example, you said this model would be good for studying filtering and
at the philosophical level.
Yeah. But like for that case, the thing will go in front but not back. So if we change it to make it that moving in one direction is more possible than the other, will it still be? Will we still be able to get some numbers?
No, so okay, see, one can try to understand that problem. I'm saying that the details of the problem will actually be different. But it's the general philosophy, some of the stuff will continue to be applicable, some of the stuff will change. So you have to see. But some general philosophy will continue to be applicable even for those kinds of models. Models of filters in 1D are rather trivial and stupid because everything gets stuck to the right end. But in higher dimensions, they are more interesting and they can be studied. I actually am not aware of good deal of work by theoretical physicists in that area. There is some little bit of work by engineers, but they don't usually do any modeling. They just randomly say, let us, no. They make ad hoc approximations or ad hoc answers saying that whenever the clogging is more than 70%, then throw away the filter paper, use a new one. No, it's a working rule, but it doesn't explain why you do this. Okay. They have adjusted the number by experimentation, optimize something or the other, but there is no theory usually behind them. And our aim is to understand the theory behind and use it to design the actual systems. Yes, sir.
What do you mean by dynamical?
Very good. So, as I said, suppose I am in some configuration, and there is a set of configurations which are accessible to me. That is called omega 1. And log of omega 1 is called, K log omega 1 is called Boltzmann entropy of this thing. Okay. However, there is another thing called all possible states which are consistent with my macroscopic information. So, for example, the macroscopic information is that I have this density of sokobans, this density of boxes, and this is the size of the system. Given this constraint, there is some configurations which are accessible to me. The number of these configurations will be called omega 0, let us say. Log of omega 0 will be different from log of omega 1 by huge amounts. And it is quite often easy to calculate log of omega 0. It is quite often very hard to calculate this extra stuff because it depends on how the breakup is occurring. I have to quantify the breakup in some way to find out how many states are accessible. And it's not always the same number. It's varying from component to component. So I have to do some average. I have to calculate an average of log of omega 1. And that is usually very hard thing to do. Like in spin glass problem, which is a very classical problem, that was the thing which bothered everybody. How do we calculate average of log of something? And so here we are. side stepping, all those kinds of issues, we can actually calculate log of omega 1 exactly in some setup. And maybe in that kind of calculation is useful in a more general context.
Any question?
Sir, in the stage three decomposition state, why are we taking E as the empty space as a separate constant of motion? Don't they depend on the Sokoban's motion?
No. So yeah, just can we bring back the stuff? It's there. No, all E's are not made capital E. Only E's which are between B's are made into capital E. On both sides, it should not have any S. Then it cannot, it will be stuck if you are in the same component. So only those E's you make capital E. Those are the constants. Other E's are not constant. They can move around. I think let me emphasize the point about the model is this. For this model, all these constants are easy to construct and even easy to explain to a high school student actually. No heavy mathematics has been used. Okay, but similar constructions will not be possible in some other problem. So it actually is a very simple model which shows some interesting features.
Constants of motion are configuration specific.
Yeah. For each configuration there is a constant of motion, but different configurations could have the same constant of motion. So, for example, in the Kepler problem, there are orbits. Each orbit is characterized by some constants of motion, and different orbits are disjoint with each other. Okay, but yeah. So, okay, I'll leave it at that. Actually,
so the space that you are associating for each constant.
Yeah.
That can be analytically tracked.
Yeah. So analytically, all of this is analytical in some way. It doesn't involve heavy algebra. These are discrete structures. So you cannot use differential calculus very easily, or at least I don't use covariant derivatives. Not making a joke, I'm making a point that lot of structure in higher order mathematics, physics involves differential calculus. But with these discrete structures, you can use differential calculus only up to some degree and not easily. And so the problem is sort of like origami is an example. In origami is the Japanese art of paper folding. So you start with a piece of paper, you fold it like this, you can produce something interesting. Okay, but the set of moves allowed is very limited. You can fold, but you cannot cut up the paper and paste again or some such thing. If you allow me to cut up paper and paste again, I can produce many more complicated the Michelangelo's statues or something, some complicated artwork which cannot be done by origami. But it's interesting to see if some of this stuff can also be done only within the setting of origami. So you use very restricted set of moves possible, and with this restricted set of moves possible, can you do something interesting?
Sorry, what I meant to ask is the number of constants of motion depends on the configuration. Because here
No. So actually, there is some other nice theorem due to von Neumann. which is this, that suppose in the end I have got this blob picture, then I can associate how many constants of motion are there in this dynamical system. This is the question. 2 or 3 or 15, can I tell? And then there is a notion of independent constants of motion. If you say L is conserved, then L squared is also conserved. That's not a separate constant of motion. So I don't ask how many constants of motion there are, I ask how many independent constants of motion there are. The word of independent is very important. And then he proved that if you take some such system and you give me constants of motion A and B, then I can always construct a different constant C such that both A and B are functions of the single constant C. So any two constants of motion can be collapsed into one, and 3 can be collapsed into 2, and everything eventually becomes 1. So what is the single constant of motion? Okay, so this construction is very easy. It says take this picture and each blob is given a label 1, 2, 3, 4, 5 up to the maximum number possible. And this number will be a constant of motion by construction. And any other constant of motion, and I know all other constants of motion, whichever you construct, are given in this blob. So all other constants of motion are functions of this single constant of motion. Okay, so that is the way the constants of motion are defined in this problem. Yeah, this is true for all discrete systems. If you have continuum systems, then the number of constants is infinite and it's hard to tell one infinity from another or some such thing. So von Neumann theorem does not hold, or it's not defined for continuum problems. But for discrete problems, this procedure works. If the number of components is infinite, then I don't really know what to do.
Any other questions?
There are no more questions. Let's thank the speaker once again. I would like to request Professor Dhar to present a token of appreciation. Yeah.
Thank you very much.